Wow, this is an interesting screen. Lots of colour. Getting into a bit of horticulture here, I think. Oh, not completely. Have a look at the title. Models of Growth, up here. Models of Growth, Part 2. And this is talking about modelling, some things in nature here by the looks of things. And we're going to look at recursion formulas. Oh, what's that? Or sometimes we call this formulae from the Latin. Recursion formulae, formulas, the plural. Anyway, so let's have a look around the screen. And I reckon we've got to look at this dude for a start. And this guy is called Fibonacci. And he was responsible for a lot of work with numbers in nature in particular. And what he was looking at was whether there was any pattern or sequence of numbers in the array of petals and numbers of petals in various species of plants. Any mathematics in this down here, in this cone? Is there a sequence of way the spirals form and so on? Over here, the structure, look at this, the structure of the leaves to catch sunlight and water and so on in plants. There are some patterns there. Okay, so this is interesting, this modelling, isn't it? Using mathematics to describe practical situations. And Fibonacci was very much into these sort of natural situations. And have a look down here. There are some numbers in squares here. Somebody's been trying to, model this. Find some mathematics in this sort of snail type shape here, or shell type shape. And those numbers here, what are they? 1, 1, 2, 3, 8, 5, 5, 8, 13, 21, 34. That's a special little sequence of numbers, and that's called Fibonacci, the Fibonacci sequence. We'll have a look at that. Fibonacci worked with this sequence and called it nature's numbers. Well, that's what people think of it as, nature's numbers, because in nature this particular sequence pops up a lot. We're going to have a look at that to introduce this topic. And over here, the seed pods in the middle of this sunflower. Hang on, we'll get rid of this one. Follows a pattern. Okay, so there's lots of things in nature. Just remembering back, of course, that Pythagoras said the world is number. He found a lot of patterns in the world and the structure of the world, and he said that. So it's an interesting area of mathematics. Come down, let's have a look at it. And here we go, Fibonacci's sequence, the nature's numbers, if you like. Here's a pattern that occurs quite frequently in nature, and Fibonacci listed it out. And so this is automatically a model, isn't it? When we list a sequence of numbers to describe a naturally occurring or a practical situation, it's modeling. Can you see any pattern in these terms? Just sit there for a minute and see if you can see a pattern. Pause the presentation and see what you think. All right, well, let's go on. It's a fairly difficult one, isn't it? Because these don't go up by anything. This goes up by 1. This goes up by 1, and then that goes up by 2, and then 3, then 5, but then that's 8. And 13. Oh, this is hard to see a pattern here. And then if you look at any particular term and say, how do you get 2, 3, 4, 5? Let's say the sixth term, n is 6. What do you do to 6 to get 8? That you also would do to, this is the ninth term. What do you do to 9 to get 34? Working on that sort of pattern. It's not an easy sequence to analyse. Let's come down and let's start some work on Fibonacci's sequence here. So there's the sequence, and one thing that you could say is that the first two terms, we're using F for the term now, and F1 is the first term, F2 is the second term. They're both 1s. And what do you notice? The third term here is the sum of the previous 2. Look at this notation. This is a bit confusing. This is the idea of recursion formulae. In other words, you're looking at how do you get this term, not from being the fifth term, but from how do you combine these others to get to there. Okay, so that's what a recursion formula is. Looking at the connection of any term to the preceding terms. So this is, you get the m plus 2th term. Nothing to do with dentistry there. Small joke. By taking the preceding, look, n plus 1 is the one before n plus 2, and the nth term, n there, is the one before this one. So we would read this as any term, and we're calling it the n plus 2th term, is the sum of the preceding 2 terms. So get your head around that. That's important. This is the idea of recursion formulae. Okay, just remember this notation. Those terms. N is the one before n plus 1, and n plus 1 is the one before the n plus 2th there. Okay, so this subscript here is the position of the term. The position of the term. So we saw that in the earlier presentation. Okay, and so you would start off with n is 1. So let's do it. If n is 1 down here, f3 is f2 plus f1. In other words, putting n as 1 in these positions here. Okay, so it's 1 plus 1 is 2, just showing that the formula works. If n is 2, you'd be on to f4, and that would equal f3 plus f2. So you would be finding this term, and it would be the preceding 2. That would be 3. If n is 3, the term you're looking at finding is the 5th one, and it's the 4th plus the 3rd. Okay, so here we're looking at, let's just tidy this up a bit up here. We're looking at finding the 5th term, which be the sum of the 4th and the 3rd. So it's 5. So that's our mathematical method of describing the recursion pattern that we see here. To get further, you've got to link the terms together, and that's the idea of recursion. Now, in a minute, I'm going to show you how to get show you the formula to get a particular term. So if you wanted to find the 13 without putting those down before, what is T7 as a direct formula in n? Okay, like we did with arithmetic and geometric sequences. We could land on a term many distances a long way down here by just putting in an n number. Can you see with recursion formulae, you can't actually get down here without doing this and building. So that's a bit of a disadvantage of recursion formulas. Okay, come down, let's look at Fibonacci's actual explicit formula in n. So when you write, there's Fn, we were using Tn before, using F for Fibonacci in his honour. The nth term in the Fibonacci sequence, oh, this is an animal. We're going to look at how to develop this later on, but it's quite a complicated formula in n. You wouldn't be able to spot it by just looking at the terms, would you? The only thing we could spot was the recursion idea. Those two gave that one. These two added gave that one. Those two added gave that one. We could only do the recursion method like this. Okay, but there is an explicit and exact, if you like, explaining exactly. Explicit means giving the detail, doesn't it? Explicitly saying what to do to n to actually find a particular term way down. Let's say n equals 100. We want f100 without using recursion. So you would stick it in these spots here and stick that 100 in there and find the term. Okay, so let's go on, and what we are focusing on now is not in this presentation so much these formulas that we were doing before, but the recursion method, how to connect previous terms together to get the next one and so on. Okay, come down and let's have a look. Here's arithmetic sequences. Can we write these in a recursion mode? Here's a formula for any term. You get the first term, which here would be 4, and you add on whatever term n take 1, lots of d, and what is d? Here it's going up by 3. So this is the explicit formula for the nth term in terms of n. What is the recursion formula? Well, how would you describe it? To get any term, what do you do to the one before? I know, you add on the common difference, don't you? Right, so any term, let's take this one here, the fourth term, T4, is the preceding term, T3, plus 3. Okay, so this is a bit of a good definition now of, hang on, we'll just pause that there. So here we go. That's the idea, isn't it, of having a formula connecting terms to the preceding one. Let's go down and have a look at the summary here. Some screen clippings from Hayes and Harris publications there. And there's our two formulas now for the arithmetic case. The one that we derived before, and now one connecting a term to the preceding one. Are you starting to notice that with recursion formulae, you must be given the starting term or terms, mustn't you? Recursion, some start point or some starting point must be given. Okay, so here you need to know the first term so you can build on it. So, and in the Fibonacci sequence, we needed to know the first two terms to build on them. Okay, come down, let's look at geometric. Here's our geometric sequence, and here's the formula that we derived before. This is a formula for the nth term explicitly in n. What could we say about a recursion method? To get the next term on from n, given a starting point, and remember what we're doing with recursion is building this way, right? Not landing on a particular term. Okay, so here, it's the preceding term. What are we doing? We're multiplying by r, aren't we? The ratio, common ratio here. 12 over 6 is 24 over 12, and that's our common ratio. So we would write any term is r times the nth term, like that. Okay, so that's a way of doing it. So if we wanted, let's say we wanted 12, that's the third term, that should be r times the term before it, which is r here is 2, so it's 2t2, and so on. We could keep going with that method. Okay, but we must be given the first term, t1, or we could call it, we've been calling that a. You'd have to be given that so you can build. Okay, that's important to notice, that little bit of a disadvantage with recursion there. You have to know preceding terms to build on them. Okay, let's have a look at doing something with this. And there's our summary from Hayes and Harris, so you should have a look at that in the book. Okay, there we go. Let's look at some examples now. So find the next three members of the sequence given by these. So you're given a term and then you're told how to build on it. Read this as any term is the preceding term, take 2.5. So if you start with t is 1, n is 1, you'll be able to put 1 in there, so that'll be t2 equals t1, take 2.5. So you can think of that as mechanically substituting in, n in this position and here, or you can think of it as n plus 1 term is a term and nth term is the one before it. Probably more universal that way. So 7 take 2.5 is 4.5. And then if n is 2, go to the next term, t3 will be t2 minus 2.5. And therefore you're going to take 2.5 off each time. Do you get the idea? You're building it from a recursion model. And here, let's say you've got a first term, and this is read as the any term is half the one that came before. So this was arithmetic with a common difference of neg 2.5, wasn't it, taking it away from the preceding term. What do you reckon this is when you're multiplying the preceding term by half? So it's a half of 24, which is 12, so this is going to be geometric with a ratio of a half, because you're multiplying every preceding term by a half. Do you get it? Study those examples, that's important. Come down now and have a look at your go. Have a go at 2A4 here. And in this presentation, it is important that you do every problem to really get your head around the recursion idea. This is used quite a bit in mathematics in other areas other than sequences. I'm going to show you a bit later on how to use the Casio 9860 Plus to tackle recursion modelling. Okay, have a look, have a go, and I'll show you the answers now. And there are the answers to those problems. So look at it carefully, make sure you get them all right. Okay, let's go on and see what else we can do. So here is another example. Find the explicit formula for Tn if we're given the recursion. So in other words, we're coming backwards from the recursion to finding an explicit formula, which is always very useful if you want to go down the sequence without filling them all in and land on T100. Okay, if you want to do that, then you need to have a formula for Tn. So let's take the recursion formula in the first term. So I don't know, I'll do it the book way here and then I'll show you another way. So if you wanted to find an explicit formula for Tn, you could subtract Tn from both sides and you'd get 7. So the difference between Tn plus 1 and Tn is 7, so that would be a common difference, wouldn't it? And the first term is 5. So the fact that you can identify there's a common difference, which is 7, from this rearrangement here means it's arithmetic, and then you can put in the standard formula. Or you could just generate the terms. You know the first term is 5, and the next term is 5 plus 7 is 12, 19, go back to basics, then see that that is first term 5, difference is 7, and construct it with the formula. You can always just substitute in and have a look, rather than just doing it with the algebra here, if you like. Okay, what about this one? We could see that it's geometric because any term is 0.4 times the preceding term, and we've got 100 here. So you could say A is 100, and the ratio, any term divided by the one before, is 0.4. So therefore we can say the general formula for a geometric is this, and stick the numbers in the holes there. Or you could just start it. The first term is 100. How do you get to the next term? It's 0.4 times the one before. So times this by 0.4 is 40. And do it again. 0.4 is 16, and so on. And then identify that that's A is 100. The ratio is 0.4. 16 over 40 or 40 over 100. And so on. And then stick it in the general formula for the geometric. So there's a few ways. Do enough to satisfy yourself that you've got your head around it and that you're up close and personal with the actual math there. Come down and do some here. So there are some where you've got the recursion formula, you want to come back and get the explicit formula so that you can go to any particular term in a sequence without building all the ones before it. Okay, let's have a look at the solutions to those now, or rather the answers. There they are, just 4 little ones. Okay, let's go on now and have a look at some other things. There's some interesting things coming up, some quite heavy mathematics, so stay with us here. Find the recurrence relationship of the sequence given by, now this time we're going from explicit formulas for Tn in terms of n and going to a recurrence relationship. So one way of doing it is to say, well, I want to find Tn plus 1, so put in here n plus 1. Okay, so here Tn plus 1 would be 5 times n plus 1 takes 6, and so we're putting n plus 1 in both places in there, and then if you simplify this, there's our first, that was our original relationship, 5n takes 6, and that was Tn plus 5. So you could do that purely algebraically. Take the explicit formula in place of n, put n plus 1 and then try and connect it back to Tn, or you could generate the terms here, and the first term where n is 1 is neg 1, and then your multiplying by 5 and taking 6. So putting in the next term, what would that be? So it would be putting in 2, that's 10 take 6 is 4, and you can see it's going up by 5 each time. Putting in 3 is 15 take 6 is 9. So you could actually use the formula to generate this and then say any term is the preceding term plus 5 by actually seeing it here rather than using the algebra. So I leave it up to you to whether just to put n plus 1 in the formula and try and connect it back, or to go and write the whole formula out, or write out all the terms and look at it from that point of view. Alright, so down here, let's have a look at the same sort of thing for geometric. What we're doing here is putting n plus 1, come back up here in that spot and that spot, and we get this expression. Bit harder to see this time. You've got to, in this position, generate the Tn term. So instead of n, it's n take 1 times another 0.8 to get a total of n as the power, and that's Tn by 0.8. So you can then summarise it as that expression there. You need a term, a first term, and then the recursion model. Or what you could do is to, for our formula, start generating the terms as I did up here, and have a look at the geometric sequence of them. Just notice that we must specify, so over here this is incomplete, this answer, we must specify T1 equals neg 1. And so when we're doing a recursion method, you must have some starting term, or terms. Fibonacci needed 2 terms to start. So you must specify a starting term when n is 1, and then try to build from that. Alright, so I think probably I want you to look at trying to do it both ways, actually listing the terms down and spotting whether it's arithmetic or geometric, and then also this algebraic idea here and here, putting in m plus 1 in place of n, and trying to connect it back. Alright, want to have a go? Let's have a go, and here we are. Find the recurrence relationship of the sequence given by, there's 2 methods, sub n plus 1, and connect back to Tn, to Tn, or list the terms and identify geometric or arithmetic. Okay, probably have a go both ways. Alright, let's have a look at the answers. There we are. So how many did you get right there? Just remember, when you're specifying a recursion, you must specify the starting term, or terms, whatever that recursion sequence requires, or recursion formula requires, and then the actual model. Okay, let's go on. There's a few things coming up that are going to be interesting for you. Okay, so here we are, given T1 equals 1, and Tn plus 1 is 2Tn plus 3, for all positive integers, find the next 3 terms of the sequence. So you start off with let n be 1, so put 1 in here, that's T2 will be 2 times T1 plus 3, there we are, and then T2, letting n be 2, would be T3, sorry, so you're putting in the n value here and here, and building. Or, if you don't like that substitution or getting up close and personal with it, you read this relationship as any term, we're calling it the m plus 1th, equals 2 times the preceding term plus 3. So that's what that is saying to us. Or you can mechanically substitute in. N is 1, n is 2, n is 3. But I want you to realise that that's what you're doing, rather than the mechanical algebraic substitution. I want you to be able to read the formula like that. Okay, let's do some now. Some of your own down here. So here we are, question 4. Find the next 3 members of the sequences defined by those. Okay, so I challenge you to read this one. What's this saying? Any term is, what do? Take 1. Okay. All right, and just remembering they're telling you the starting points here so that you can build. Recursion formula builds on preceding terms, and that's what we're doing here at the moment, getting up close and personal with that. Okay, let's have a look at some answers. There are answers there, so make sure you can get those and understand it. Okay, let's go on. Here we have another little doofy we're doing, and of course here, can you see what's happening? They're giving us 2 starting terms, so this is like the Fibonacci sequence. It needed preceding 2 terms to move on. And here it's saying any term, we're talking about the n plus 2 term here, is the preceding one, right, because this is 1 less as a subscript there, so that's the term before the n plus 2, and plus 2 times the term before that again. Just keep in mind, if we're going along a sequence, there's the nth term, that would be the n plus 1th term, and then there's the n plus 2. So this is a way of saying to get any term, you've got to do something with these 2. That's why down here they've given us those 2 values. And what would you say in words? It is the term before plus twice the term before that again. Okay, so if we've got 0, let's do it down here, 0 and 1, the next term, here we are, n plus 2 will be this one plus 2 times this one. So it'll still be just 1. Then the next term in here will be this one plus 2 times this one. So it will be 3. So you can do it that way, or you can mechanically substitute in, put n is 1 in there, you get t3, is put n as 1 in there is t2, put n as plus 2 times t1, and substitute the numbers in. I would like you to get up close and personal, again I'm pushing this a bit, with the formula and being able to read what this means. That is, looking at the actual relationship in numbers along a sequence in positions and what you do to them to get the next one. Okay, so letting n equal 2, you would have T4, T3 and 2T2, and you're building them, okay? And you can write them out like this so you can see what's going on. And then finally, n is 3 will give you the number 5. So just have a look at those 2 ways of thinking about that. Okay, let's do some. Here we are. Now, there's a few things happening here. So going to have to think about this, and I want you particularly to scratch your head about some of the things that are going on here. We've got some conjecture here. What do you suspect from your answers in part A? That's in this part here. So this is getting a bit more challenging. So I want you to think about it. This is just the mechanics of what we were doing before. But down here, they are asking you to think a bit. If I list the first 20 terms, that's just using the recursion method. And then it's important that you check out this formula. All right, so pause it and have a go. I'll show you the answers. Okay, so there we have the answers. And did you get everything there? Just particularly noticing that one there. Okay, you might talk to your teacher and classmates about some of that. Okay, let's go on and finish off now with some work on the calculator. This is question 8 from the textbook. I do want to go over this reasonably carefully. So consider the sequence T1 equals 5, and there's the recursion formula. Oh, that's pretty ugly. Can we read it? Any term is a half of the preceding term plus 7 over the preceding term for positive integers n. Obviously, this is a sequence where n is the number of the term, and it's got to be a positive integer. So it's starting with the first term and going on to the second, third, fourth, etc. Now, use your calculator to find these 6. That's the quickest way. Particularly when you've got an ugly looking recursion formula like this. Can the calculator do it more quickly? Well, of course it can. Now let's see how to program that. So, come to this first screen over here. So turn the Casio 9860 Plus on and you come to the menu. I want you to highlight Recur in there for Recursion Formula, and this window comes up, and if you push execute, you get this window and it's ready for you to put something in there. Can you notice AM plus 1, not TN, not FN plus 1. So it's AM plus 1 in calculator land, A, B and C. We're only going to use the A, and we're going to enter something in here. What do we want to enter? Well, we were talking about the n plus 1th term, so we want to enter the nth term. Where is it? Here it is down here. AN is the preceding one, so you'll hit F2 in there. Okay, so that you put AN in this position, and then you've got to do all this. So AN plus 7 on AN, all in brackets, divided by 2, or half of that. So that's just repeatedly accessing that button to enter that expression. Bracket AN plus 7 divided by AN bracket divided by 2, and then it will give you that form there, or a half of AN plus 7 over AN. So it's an interesting little node on the calculator there. Alright, so once you've entered it and it's highlighted, so that's this line here, what we need to do now is to set it up. And so we've got here set there, which is hitting F5. So if you do that, we've got the setting here, and you've got to tell it what to start with. So we've got T1 was given, T2 to T6. So we have to over here, well, notice we're doing a table setting n plus 1, so we'll start with 1, and that will give us T2, and then end at 5. 5 plus 1 is T6. So you're actually entering the n values in here to give the n plus 1ths, if you like. So you start at 1, which will give you the second term, and through to 5 to give you the sixth term. So a little bit different here. And if you execute that and then ask for the table to be drawn, so that's F6, then you get this table. And the first term here is the second. The first term in the table is the second in the sequence. So when n equals 1, this is the 2th term, n plus 1th term. Okay, so here we keep going down, and of course that's a very easy way of generating the terms from a recursion formula without repeatedly substitution in and adding them up yourself or that sort of thing. So please keep that in mind, this calculator use of for recursion problems, because there are other areas in mathematics where we use a recursion approach, and it's going to be useful there. All right, so we're on question 8, and that's the way to do question 8, part A. Let's go back up. There it is, part A, to find that decimal formula. Okay, so list all those out. Those first 6, we're going to use them in part B. So come down now. Here we are. Oh, we'll just put them all up, I think. Yeah, okay. So here's the rest of question 8. Find root 7 using a calculator in run mode. And what do you notice? What's the connection between that and part A? And then keep going and make some observations here. This is interesting, this pattern of what we're going to come, what's going to come out of this recursion formula of AN plus 7 over AN divided by 2. All right, now down here is a bit of a challenging problem. So I want you to think really hard about question 8 and 9, because they are important for you to now develop what is basically a fairly straightforward pattern idea into a little bit more challenging maths. So, all right, have a go, and I'm going to show you the answers now. So there they are. Study this carefully and see what you come up with. And we're going to keep going with sequences and series, and it's an interesting method of modelling in mathematics. But for now, it's cheers from me.